have you back with us for another video on Moocor series. We are starting Module 2 of Moocor. This module consists of topics 4, 5, and 6. And it will discuss the solution strategies that we have for linear programming problems. In Module 1, which consisted of topics 1, 2, and 3, we worked with a two-dimensional problem. Most cases that were discussed were problems of two variables, simply because we could have plotted the problems, and using a visual representation of the model, we were able to discuss many important concepts and characteristics of the linear programming problems. We went through feasible region, objective function, graphical method, standard form. We discussed the characteristics of the slack variables, slack or surplus variables. We discussed many issues related to the individual extreme points, the concepts of adjacent extreme points, and so on. And at the end, we came up with an idea of how the solution strategy should be. And that was main ideas about the solution strategies for solving linear programming problems. Topics 4, 5, and 6 are exactly going to be doing that. We are going to introduce to you a solution strategy known as Simplex method. The Simplex algorithm follows basically the same ideas that we introduce at the end of topic 3. In this method, you start from a basic feasible solution and you move to an adjacent basic feasible solution such that the objective function improves. We will continue these movements from one basic feasible solution to an adjacent one to that basic feasible solution until we reach a point that no more improvement is possible. At that point, we claim that basic feasible solution to be the solution to the problem, and the objective function value associated with that basic feasible solution to be the optimal solution of the problem. Seems very easy. And actually, it is very easy. The algorithm has several steps. We are going to show you the steps required for the algorithm. But before we start actually using the algorithm, I would like to take you back a little bit and elaborate on that solution strategy. My goal in Moocor is to show you why we are doing the specific steps. Instead of trying to memorize how they are done, if you know exactly why they are done, it's much easier to apply them. Now, in Module 1, most of our discussion was on two-variable problems. From here on, most of our discussion is about multivariable problems. However, once in a while, we come back to examples of two-variable to elaborate on some specific steps. There is also a wealth of information around on internet. YouTube by itself has many videos that you can use. My channel has many videos that have been recorded during class sessions and as tutorials developed after the classes to help the students. Take a look at them because it fits perfectly with what we are doing in Moocor. So let's start with an example problem. Convert it into a standard form, and from there, let's see what we can do. In this problem, we have a maximization problem with 4 variables and 3 constraints. All variables are greater than or equal to 0, and all 3 constraints are less than or equal. We will write the standard form of the problem, and we will reorganize it such that all variables are written underneath each other. That way it's easy to recognize the set of coefficients for any specific variable. The main set of equations are the 3 equations in the middle. We have 7 variables, 3 equations, and 3 equations requires 3 basic variables. The other 4 variables are going to be non-basic variable, and they will be assigned the value of 0. Clearly notice that x1, x2, x3, and x4 are good candidates for non-basic variable set, and s1 and s2 and s3 can easily be calculated for our solution value. With this information, the z value will become 0 because all x1 through x4 values are 0, so z will be 0. Now we need to check to see whether this solution is optimal or can it be improved. Let's look at the objective function of the problem. Non-basic variables x1 through x4 resulting in z0. Now the question is, can z be improved by moving from this extreme point to an adjacent one? If so, which one? Remember that our set of non-basic variables x1 through x4 and basic variables s1 through s3. One of these non-basic variable will become basic and another basic variable will become non-basic. But which one? That is the question that we need to answer. Let's look at the objective function. Can z be improved? Yes, by increasing the value of any non-basic variable from current 0 value to a positive value. And as you notice, the x2 has the most positive coefficient, so by increasing that we will have a better z value. In a standard form, that most positive become the most negative coefficient. So our entering variable in this case will be x2. Which one is the leaving variable? Consider one of the constraints. For example, this constraint x1 3x2 plus x3 plus 3x4 plus s2 equals 24. Can x2 be increased 1 unit? Yes. Can it be increased 2, 3 units and so on? Can it be increased 10 or 20 or 100 units? You notice that as we increase the value of x2 beyond some limit, it makes the slack variable negative. So there is a limit. And what is that limit? That limit is actually the ratio of the right hand side to the coefficient of x2. And if we look at all 3 constraints, all 3 equations that we have, and find that ratio for each one of them, we will notice that the maximum that we can increase this value comes from a minimum ratio among these. That suggests that on the 3rd equation, if I increase that beyond 4, then the basic variable on that, which is s3, will become negative. So s3 will be the variable that leaves the basic variable set. So our old solution, which was x1, x2, x3, x4 non-basic and s1, s2, s3 basic, now becomes x1, s3, x3 and x4 non-basic and s1, s2 and x2 basic variable. Notice that these are adjacent feasible extreme points, but the new solution has a better z value of z equal 16. So the answer that we were looking for is that solution, the old solution, is not optimal value because we found a better value for that. As we looked in our case, what were the challenges? The challenges were how to find a feasible extreme point to start with, and we selected the origin to start at that point. We will later on look at the cases that the origin cannot be selected, but at this topic we are looking at the ones that the origin can be selected as a feasible extreme point. Now, the second challenge that we had was which adjacent feasible extreme point to choose and how, and the one that improves the objective function was the answer for us, and that selection was through the mean ratio. Now, how to guarantee that that solution that we have come up with is optimal? To do this, we first need to learn how to update the problem, going from the old solution to the new solution. So this is how we do. In each one of the problems, you notice that I have a basic variable. In second one S1, third one S2, and the last one S3, and of course on the 0, Z is always the basic variable, and it remains as basic variable throughout. Notice this structure of the problem. In each one of these constraints, I only have one basic variable, and that basic variable appears only on that constraint, nowhere else. All other coefficients of that variable, basic variable, are 0. We would like to keep the same structural design at the new solution. So we are going to perform some steps such that we will keep the new solution in this organization format. And what is that organization? This structure says that S3 had a 0, 0, 0, 1 coefficient set. I would like to have the same type of organization for my new basic variable, which is going to be x2. But I notice that I have -4, 1, 3, and 2. How would I convert this to 0, 0, 0, 1? Using row operation. So let's look at the steps that we are going to be taking for row operation. Again, as I said, instead of using the complete set of the problem, I only use the coefficient. So this is the same problem written just with the coefficients of that of the variables. Now S3 is the one which is going to be leaving the basic variable set, and x2 is the one that is going to be entering into the basic variable set. I would like to change these coefficients by using row operation to have them as 0, 0, 0, 1, the same structure that S3 has in here. The row operations require several identification for us. First is to identify a pivot row. That is the row of S3. A pivot column. That is the column of X2. And their intersection, of course, is the pivot element. All of our calculations are based on this pivot row and that pivot column and the pivot elements. So in row operation, what are the legitimate steps that we can perform? The legitimate steps are multiply a row by a real number, and the other one is multiplying a row by a real number and adding it to another row. Just these two will take care of what we want to do. So we have 0, 0, 0, 1 as our goal, and we notice that the pivot is 2 and it needs to be 1. So we can multiply this row by 1/2 and the result will be the new row, and this new row belongs to the new extreme point. But we are still not done. The next set of operations are to convert the other column elements of pivot column. Now we have 3 and we need to make it 1, so we can multiply the pivot row, the new pivot row, by -10. The next one will be the other element of x2 column, which is 1, and it needs to be converted into 0, so it is easily done by multiplying the updated pivot row by -1 and adding it to that row. And finally, the -4 that we have on the z row, we need to convert that also to 0. So we are going to multiply the new pivot row by 4, by +4, and add it to the zero. Now you will notice that we have accomplished what we were looking for. Now let's look at this new tableau that we have. Each one of these rows are representing an equation. For example, the first one is 1z minus 3x1 5x3 minus 2x4 plus 2s3 equals 16. The same is true for the rest of them as well. The second row will be 2x1 minus 1/2 x3, 2x4, 1s1 minus 1/2 s3 equal 12, and so on for the other two rows. So our new problem, which is the same problem except it is written in a different format. Now you notice that the basic variables s1, s2, x2, and of course z, as always, are in the same structural format that we were looking for. The new solution, of course, is x1 equal x3 equal x4 equal s3 equals 0. Those are non-basic. And s1 equal 12, s2 equal 12, and x2 equal 4 with the z value of 16. Now, what we did, we actually performed one iteration of the simplex method. So let's see what we have done. We have converted the problem into a standard form. We identified a feasible extreme point. We identified basic and non-basic variables. We checked to see whether that solution was optimal or not. And if solution were optimal, we would stop. Otherwise, we move to an adjacent extreme point, which will provide a better solution for us. Now, the question is whether this solution is optimal or not. The current objective function rho is z minus 3x1 plus 5x2 minus 2x4 plus 2s3 equals 16. Notice that there is a negative coefficient. There are actually two negative coefficients in there, so we can still improve the value, and x1 is the better one because it has a more negative coefficient. So we are selecting x1 as entering variable. Now we need to identify the leaving variable, and we do that through the min ratio. Now notice in here that the third constraint does not have any x1 in it. The coefficient of x1 is 0 in there. So x1 has no impact on that constraint. So let's continue just like the same steps that we did. We will do the process as before, and we come up with the new solution. As we come up with this new solution, by looking at the 0, we notice that there is no negative number in there, so it cannot be improved. So this solution is actually an optimal solution. The same structure that I use here can be formalized into a Simplex Tableau. It is the same problem and the same table that you just saw, except that now I have organized it and I have partitioned it and separated it such that the basis is identified, the variables are identified, the right hand side is identified. It's in a better representation format. I write the solution underneath. I will ask whether it's a optimal solution or not, and if not, I will identify an entering variable, and by taking the min ratio I will identify the leaving variable, and I identify the pivot row, pivot column, and pivot element for that tableau. Now let's do a complete problem, but before we begin, remember a few things. One, if there is a tie breaking, you can do an arbitrary selection. If there are two numbers that are the same, you can select any one of them. Do not calculate the ratio for the rows that their pivot column element is negative or 0, because they don't have any impact on that equation. Do not round off numbers. Use only fractions. That would stop a lot of errors that you might incur during calculations. And the optimal solution is reached when there is no negative value in the 0. So steps are pretty simple. In this problem, I have a maximization problem with 5 variables and 4 constraints. All variables are greater than or equal 0. All constraints are in the form of less than or equal sign, which clearly would identify my starting basic feasible solution as the origin. I will write the problem in standard form. I will add slack variables s1 through s4 to the problem. Again, now I have 9 variables, 4 constraints, so I would have 4 basic variables and 5 non-basic variables. My non-basic variables are my x's, and my basic variable are the s's. So the first tableau, the first simplex tableau, is presented in here. I'm identifying the entering variable. I'm identifying the leaving variable through the regular means, which means the most negative in the 0 is selected and the min ratio is selected. Now I have my pivot row and pivot column and the pivot element, so I can perform row operation and move from this solution to the next solution. This is the next tableau. I have performed 1 iteration. Again, is this solution optimal? No, because there are negative values on the 0. I have a -7, which is the most negative number that I have in there. So I'm identifying x3 as entering variable. Through the min ratio, I am identifying the leaving variable, and the pivot element, I will perform another row operation to get to the new tableau. In this tableau, again, I will notice that the solution is not optimum. On the 0 under x2, I have a negative value. So x2 is my entering variable, and through min ratio, I identify S1 to be the leaving variable. Just look at the min ratio column and notice that on the second one I'm not actually calculating any ratio, because on the pivot column the number is -1/5 and it is negative. So I will perform another set of row operations, and I will move from this tableau to the next tableau. In this tableau, I notice that all elements on the 0 are positive. So this tableau is representing the optimal solution. You can read the solution from the bases and the right hand side. x2 is 8 and 12/13, x3 is 11 and 5/13, x5 is 13 and 3/13, S4 is 2 and 10/13. The right hand side value, which is the z value, is also identified. Let's do another example, but this time I'm doing it as a 2-variable problem because I can plot it. In this maximization problem, I have 2 variables, 4 constraints. I have written the problem in a standard form, the first tableau, the second tableau, and so on are drawn. Notice that each tableau represents an extreme point, and these are the adjacent extreme points as we go from one tableau to the next tableau, as we are moving toward the eventual optimal solution. In this case, this tableau represents the optimal solution, and as you see, the process was very simple and straightforward. How to avoid errors is practice, practice, and practice some more. Avoid round-off errors, use fractions, it always helps, and be very organized in your calculation. Also make sure that you have selected the right pivot before you generate the new solution, and of course the values of the variables are always positive, so make sure that there is no calculation error or wrong mean ratio selection. Ahead of us, we will be looking at the topics 5 and 6, in which we will discuss the cases that the origin is not a feasible extreme point, and of course we'll be looking at the simplex tableau mathematical structures. Thank you for watching this video. See you next time.